Today's topic is electromagnetic waves. Now we have seen magnetic field, we have seen electrical field, but we have never seen a situation wherein both are present together usually. So this is so in case of electromagnetic waves. Now, what are electromagnetic waves? Electromagnetic waves look something like this. There are two waves. If you can see, one is in one plane and another is perpendicular. They both are perpendicular to each other. For example, the red one is the electrical field, which constitute the electrical waves, and perpendicular to that is the magnetic field. So the first thing is that electrical field and magnetic field, they are perpendicular to each other. And they are also perpendicular to the propagation. So this is the direction of propagation, and electrical field is perpendicular to magnetic field, and both are perpendicular to the direction of propagation. And they exist together, right? Now, in a electromagnetic wave, it consists of two waves. One is electrical and another is called the electrical wave is represented as E as E naught this format we have seen many times earlier. Similarly, the magnetic field is represented as B here. C earlier was the velocity of propagation. Here this is velocity of light, because the speed of propagation of electromagnetic wave is the speed of light. Now, let's revisit Ampere's law. What it said was, you take a loop integral of B dot dl. This is going to be mu naught I. There was a caveat in this relationship, and the caveat was that provided electrical field is constant. This is a big condition. Now, if you take the case of a parallel plate charging, maybe through a resistor or whatever, the charge on the parallel plates are not constant. It keeps increasing. And there are many examples wherein you will find that while you can apply this formula, Ampere's law, but the field may not be constant. So what do you do? It has been found out by Maxwell that the actual corrective Ampere's law would be like this is the loop integral would be plus another term which is called displacement current is added, and this is on account of change in magnetic electrical field. So this is this term is the flux of electrical field, and which is nothing but electrical field into area. This one. And the rate of change of this flux into epsilon gives rise to a current called displacement current. Now, in a parallel plate capacitor, the current that flows here is called, this I is called conductive current. This current is present only on the outside of the capacitor and not inside, wherein displacement current is only present within the gap of the plates, and it is not present anywhere outside. So they are sort of mutually exclusive. Now there is a direct relationship between electrical field and magnetic field. And the relationship goes like this. Electrical field is equal to C times magnetic field. This is velocity of light. This is the magnetic field. This is the electrical field. Besides this, there's another relationship, which is velocity of light is expressed as 1 over mu naught into epsilon naught under the root. These are two relationships. One is this and one is this. Now, since it is B naught, this is maximum amplitude. And this also is maximum amplitude. Or rather amplitude. There's nothing called maximum amplitude, or it is also called a peak value. Peak value is what we've seen in this station. This is called peak value. Both are peak value. These are instantaneous values at any time t. Okay. Now let's try to calculate energy density in these two fields. We know this is energy possessed in an electrical field divided by the volume. This becomes the density. Electrical energy is defined like this, and this is equal to half epsilon E square. Similarly, we define magnetic field energy, magnetic density. This is magnetic energy is given as B square over mu naught. Now the total energy would be possessed by a electromagnetic wave would be the sum of the two. Right? If you want to write it in terms of instantaneous values, you can do that. This is total energy is I, and this would be V naught square sine square omega multiplied by again similar thing, V naught square sine square omega. I will write this whole term down below, multiplied by half and B is the instantaneous value, which can be written as in terms of peak value T minus x by V. V is actually velocity of light. Now we've seen that sine square theta over a cycle, average value of over a cycle is 0. Okay. So, sorry, it is not 0. It is over one cycle is half. So what we get is total energy is equal to half naught And this was not even, this was epsilon. So this is actually epsilon naught to V0 square by 4 2 plus square by 2, right? So this actually becomes this is our total energy, and we can convert E to B or B to AE by this formula. E is convertible to B and B is convertible to E. Okay. So if we convert them into one field, then what we get is, let's convert it to magnetic field. This becomes now we also know C square is given by this formula. So if we substitute C from here, what we get is average, we get is we're replacing C square with this term. So what we get is this will be what it is. This is our formula for total energy possessed by an electromagnetic wave. This is the average density. This is energy density. Average. Okay. Similarly, if you don't like, if you want to write it in terms of electrical field, you can do that also. And if you write it in terms of electrical field, the value will be epsilon both are same. Now what we do is consider cylinder the electromagnetic waves enter here and it travels with this, its velocity is c. So in delta times, how much it will travel? It will travel delta t distance. Let us say area of the cross section is, so in delta time t, volume swept will be C delta T, length into area. This is the volume swept. And how much energy it would carry? It will carry this into the energy density. So energy contained in cylinder would be how much? This is the volume times the average energy density. So if we define a term called intensity, which is, we define intensity as the energy passing or falling, whatever you call it, per unit area per unit time. This means an intensity is equal to the energy. Let's say if we take any surface or whatever, how much energy is passing through this surface on a unit area basis and in unit time. This is called intensity. So our intensity becomes per unit area and per unit time. Okay. So we knock off C U average. So intensity, which was C U average, can either be written in terms of electrical field, or you can write it in terms of magnetic energy field, magnetic energy. Both are equivalent. Then we define another term called momentum of electromagnetic wave, which is defined as total energy divided by C. This is total energy this is velocity of light. Now, looking at this displacement current, this phenomenon was discovered by Maxwell. So Maxwell wrote another equations, a set of equations. We call them as Maxwell's equations. And what are those? First is a repeat of some previous equation we have seen. Gauss law for electricity, E dot ds is equal to, you've seen it earlier, Second is Gauss law for magnetism, which is B dot ds. There is no such thing, so this is 0. The dot product of magnetic field over its surface is 0. Third is Faraday's law. What it says is E dot dl over the loop is d by dt. And lastly, Ampere's now Maxwell slightly modified Ampere law to get away with the condition that the electrical field should be constant. It may not be constant. If it's not constant, we can still use B dot dl over the loop as this was our previous expression plus a displacement current, displacement portion, which is now this portion epsilon we have seen it earlier, it's called ID. Is the displacement current, and it's purely on account of changing electrical field. If electrical field doesn't change, then the Ampere's original law need not be modified. But in case there is the electrical field within this loop is changing, then we need to add this term, not otherwise. Now next we see what are the sources of electromagnetic waves. Sources. We've seen a static charge produces only electrical field. Nothing else. A static charge will produce only an electrical field, nothing else. Similarly, a charge in uniform motion or like a steady state current steady current it produces only magnetic field. What it says is that if you have a static charge not moving, we know a static charge will have magnetic field depending upon distance from the charge, nothing else. Similarly, if a charge is moving, then it produces magnetic field. This we have seen. Still, we have not been able to generate electromagnetic waves. How do we do it? And an accelerated charge produces electromagnetic wave. If a charge is accelerated, that means not moving with a uniform velocity, it's accelerated, then it produces electromagnetic waves. Or an oscillating charge will produce oscillating electric field. And since the electrical field is oscillating, it will produce magnetic field. So an oscillating charges first will produce oscillating magnetic electrical field, and then an oscillating electrical field will produce magnetic field. So both the fields are produced by a charge which is oscillating. Okay. And the frequency of electromagnetic wave so produced shall be equal to frequency of oscillation of the charge. Okay. And now there's I'll show you some electro spectrum. You have whole range of electromagnetic waves produced depending upon the frequencies of that. So if we talk about gamma rays, this range of frequency is 2 hertz. Then comes X-rays. Frequency is 'UVs between 10 to 17 to 10 to 15 hertz. They are all hertz. UV visible light falls in the range of 10 to 15 to 10 to 14. Then you have IR. It goes from 10 to 14 to 10 to 12. Microwave. It goes from and so on and so forth. Goes up to AM, amplitude modulated waves, which are 7 to 6 hertz. So this is a whole spectrum of electromagnetic waves. Depending upon its frequency, we categorize into different categories. Yeah.